Oh, hi, everyone. Let's get started on our module number 1 of FE exam for civil engineering, geotech portions. Number 1 module is the phase relationships and soil index properties. So here is the FE reference menu. In the geotech sections, when you start, it shows you the phase diagram. So it is very important to understand the phase diagram. So the phase diagram shows us 3 different phases of soils. When you have soil samples, you can break down into 3 phases, which is air, water, and solid, as you can see on the figures. Another very important usage of the phase diagram is it serves as a bridge between the weight and volume. And for each weight or volumes, it has different parameters based on the 3 phases. Very obvious when we have the air, we have volume of air V sub A, for example, the volume of water V sub W, and the solid V sub S. Similarly, for the weights, sometimes some problem we use mass. The difference between weight and mass is weight equals to the mass times the gravity. So with a different of constant of gravities, mass and weight is interchangeable in phase diagram. It's the same thing where I like when we have a solid is WS and the water is WW. And one key things between difference between the weight and volume here is the weight of the volume of air is 0. So this is always 0 for engineering purpose. And for the volumes, be very careful. V sub A right there, volume of air it depends. It's not necessary equals 0, but it can be. So volume of air is equals 0 when the saturations of the soil is equal 100%. Yeah, as here stands for saturations, if it is less than 100%, then volume of air is no longer equals 0. And other more parameter here is the void. So in the phase diagram, the air and water make up the void within the soil matrix. So volume of void here is equals to the volume of air plus the volume of water. For the void, in terms of weight or mass, all the void goes into the weight of the water. And very obvious here for volume and weight, if we add up all the components there, the total volumes will be equals to the volume of air plus volume of water plus volume of solid. For volume, for the weight of the soils here will be only make up of 2 parts. The total weight will be equals to the weight of solid plus the weight of the water. So this is a quick overview of the phase diagram. If you want to learn a little bit more details, please reference to my Geotech CE 366 lecture. You can find the link in the descriptions. Earlier, as I said, the phase diagram serve as the bridge between the weight and also the volumes. And to serve as a bridge, there's a very important components. First, for at the water phase, always remember the unit weight of water. So the unit weight of water, the definitions is equals to the weight of water divided by the volume of water. And unit weight of water is a constant, which is 62.4 pounds per cubic feet, or 9.81 kilonewtons per meter cubed. So since this is a constant, so this powerful in a way that once you know about like either the weight of water or volume of water, you can automatically find out the other one, since like you know the unit weight of water. So that's why, like, always think of in a way that this serves as a bridging, connecting the weight of water and the volume of water. You know one, and then you can find out the other one. So it helps you to solve the phase diagrams problems. Similarly, sometimes like if the problems give you mass, not weight, then you may want to use, instead of the unit weight, use the density of water. So density of water equals to the mass of the water divided by the volume of water. And density of water is again constant. It's 1 gram per centimeter cube. So that is the bridge between at the water phase, and also for the solid phase, very important. Think of the G sub S, the specific gravity. Like the unit weight of water, G sub S is also can serve as bridging the informations of volumes and weight. Because, for example, the definitions of specific gravity is the unit weight of the solid reference to the unit weight of the water. And we know that the unit weight of solid is weight of solid divided by the volume of solid. And if we reorganize these equations, then we have the weight of solid divided by volume of solid times the unit weight of water. And this equals to G sub S. And we know the G sub S when it is given, and also we know the unit weight of water is a constant. So again, it serves as a bridge in a way that either the weight of solid or volume of solid, you can always find the other components. So that's why this is powerful when we solve the phase diagram problem. And we further move on to the formulas on this FE menus. Some of them are very obvious. We already covered it already. The volume of void, the volume of void equals volume of air plus volume of water. Always learning by heart when we talk about unit weight. It is the weight over volumes. And when we get the saturated unit weight, so when we talk about saturated unit weight in the FE problems, think of this formula. So here, the saturated unit weight is involved the specific gravity and also the void ratios. So by looking at this formula. And here it also reminds you, again, the unit weight of water. So it's handy for the FE manuals to tell you that. And for this effective submerged unit weight is equals to the saturated unit weight minus the unit weight of water. And there's always a pi here. So whenever we see a unit weight come with a pi right there, it means the effective buoyancy rate. So it's always like by the affected by the water buoyancy force. So that's why we use the unit weight of water there. Other definitions for unit weight of solid will be equals to the weight of solid divided by volume of solid. For the dry unit weight, it will be equals to the volumes of solid divided by the volumes. So be careful on when you talk about different kind of unit weights. Pay very attention to what kind of volume that you reference to. So for the dry unit weight is its total volume. But when we just talk about the unit weight of the solid, then it is just the volume of the solid. Another a key concept here is the water content. Water content means the weight of the water reference to the weight of the solid. So remember, like if I have done water content tests in your geotechnical engineering class, the water contents test, you get a wet soil samples and then you put it on a tear or a container, and then you dry up the soil samples with the container in the ovens for 24 hours, and then you take it out, then you get the dry weight of it, and with all this informations, then you can find out the water content. So water contents for water content test will be equals to the weight of the wet soil minus the weight of a dry soil after oven dry, and then divided by the weight of dry soil minus the weight of the container or the tear. So and also usually we multiply 100%, so you represent it in terms of percentage. So if you look at this formula, the top pretty much the weight of the wet soils minus the weight of the dry soil just give you exactly the weight of water, and in the bottoms you subtract the two difference, so the dry soils on top of the container, and the difference between the two will give you the weight of the dry soil. So that is how we measure water content for soil samples in the lab by using this formula. The other one is the specific gravity, which can be in terms of the unit weight of the solid divided by the unit weight of water, and we have covered it. And if we reorganize the formula, it can be written as this one. So it's the same thing on FE menu there. And the key concept is the void ratios. So void ratios is try to represent the volume of void respect to the volume of solid. So that is the definitions of volume of void ratios. Another key term is porosity. So porosity is very similar to the volumes. We try to describe volume of void, but this time we reference to the total volumes. So porosity is the volume of void divided by total volumes, and it can be represented by the void ratios too. So the void ratios and porosity, they are interchangeable. And if we play around with the equations there, we can get void ratios equals to the porosity divided by 1 mass minus the porosity. So another handy formula right there to relate void ratios and porosity. And another key concept there is the saturations. So saturations is a parameters to describe within the volume of void how much of this is air. Remember in the phase diagram we talk about the volume of void is made up of volume of air and volume of water. So from this proportions, if all of them are volume is all saturated, all of them are water. In that case, there's no air, then we call it saturations equal 100%. In that case, there'll be no air, and the volume of air equals 0. So in that case, volume of water equals volume of void. So S equals 1. And that's also another formula here. It's very easy to remember, and also it's very useful. We can remember this formula this way. George Washington is a soil engineer. And for the case that we have 100% saturations, if this is equal 1, then void ratios can be related to the water content. So W here is the water content. So the void ratios, if we want to find it, as long as we have measured the water content and it is known or given specific gravity, then at 100% saturations, the specific gravity times the water content that you measure will be equal to the void ratio. And another, if we move on this list, another part is the relative density. So relative density can be calculated in the formula below, but beware that when we talk about relative density, then we are focused on coarse-grained material, which is for sand and gravel only. So for sand and gravel type of soil, we want to know the from the given density in the field, we want to know how is this compared with the absolute maximum and absolute minimum. So in practice, what we do is we get a soil samples from the site. So at the field conditions, we know the density, but yes, we know the rate divided by volumes. So we know the density or the mass over volumes. So which divided by volume, we get the unit weight at the field. And also we know that we can either calculate density or the unit weight. So after we make that measurements in the field, we take the soil samples back to the lab and we conduct a maximum density test, or we do a minimum density test. So through those tests, well, maximum density, could be a shake table test. You have the soil samples under weight and vibrations, and after vibrations, you achieve the most possible dense samples per ASTM standard. Then you can calculate the maximum density. And for minimum density, for the same type of soils, you try to prove-viate the sand in confined volumes or predefined volumes as loose as possible. Then you can calculate a minimum density. And with that, we have the two reference. We have the at the dry conditions, we know the maximum density, and also at dry conditions, we know the possible minimum density. And with those two parameters, and also the measurements that you make from the field, with those three numbers, then we can calculate the relative density. So if it is have already like a process in terms of void ratios, then we can use another formula. But if all the math or all the information is given as unit weight, then you can use the other formula. And again, this is just for the coarse-grained material for sand and gravel only. But when you have clay materials, when you want to check the density, we call it relative compactions. So back to the our Geotech lecture, C366 compactions lecture, we talk about the compaction curve. So for clayey soils, for both clayey soils or sandy soil, but this is particularly more useful for cohesive materials like clay or silt. The density of that type of soils highly depends on the water content. So at different water content for given volumes, we can achieve different like a dry density. So the compaction curve is try to reconstitute the get a given volume soil samples at different water content. We want to find out what kind of density we can achieve, and with a couple more tests and at least like a 4 to 5 tests results, 5 to 6 test results. You do a compaction test at different water content. With those results, we can construct what we call the compaction curve. And the maximum point of the compaction curve, we call it the optimum water content or the maximum dry unit rate. So this is maximum dry unit rate. And we do this like a compaction test in the lab. And with this like a compaction test informations. So this piece of information can be used as here. So the maximum dry unit weight. So pretty much this is the lab measurements, and then compare with the field measurements, because at the lab we are able to achieve the maximum possible density at the optimum water content, especially true for clay or silt, those cohesive materials. The density highly depends on the water content. So you compare your field unit weights with the maximum possible number you achieve in the lab, that gives you the relative compactions. So we continue work down the formula. The other very important concept here is the plasticity index. We have the liquid limit and parcel limit, and a quick review on what is liquid limit and parcel limit is again especially true for a cohesive soil. For mainly this is for clay soils. The volume of clay highly depends on the water content again. And we have different status for clay. So when we have a zero water content, the clay would behave like a solid. And if we keep adding water on the clay sample, at some point, if we keep on continue to add it, the volume will start to increase, because the void filled with water, and then start to expand with like additional water, and the soil start to behave like a plastic material, not just solid, but plastic. And at the interface between solid and plastic, the water content threshold is the parcel limit. And if we keep water on it, the soils will start to feel like butter jelly, and keep adding water, it can become more soft and soft and soft. And at some point, it will act like liquid. And at the interface, when the soil start to become liquid from plastic, we call that threshold water content be the liquid limit. So that is the liquid limit and parcel limit here. And that's another index here we call PI, plasticity index, which is the difference between the liquid limit and parcel limit. We call this to be PI. So furthermore, on the soil index properties, there's coefficients of uniformities, and also the coefficients of curvature, and it depends on some additional parameters on the grain size distribution curve. So we will come back to this when we do some example problems, when we look at a grain size distribution curve together. But at this point, I also want you aware of that those soil classifications parameters, you will see them again in the reference manual. In the reference manual at the back, there's two reference, and one reference is the ASTM D2487 in your FE reference manual, page 267, and they talk about the C sub U and C sub C, and those are the same equations right there, and those are used for soil classifications. We will do some like a soil classifications problem together, but this table here, or this reference here will be handy when we get to your soil classifications problems.